Oh, this is amazing. What felt like the whole goblet vibrating is actually the rim bending back and forth, 337 times a second, the same rate as the sound waves. If I draw in the sound waves, you can see what's happening. One wave comes out of the speaker and pushes the side of the wine glass. The glass bounces back just when another sound wave pushes it again. If the timing or frequency of the sound waves is exactly right, the motion will build until the glass breaks. This is where the initial fracture happens, right nearby the speaker. We see this crack go along the bottom where the glass gets thicker and come right back up to the top where it's thin. So if we follow that a little more, 300 hertz, 300 vibrations per second, influenced by the speaker, but the speaker is way too far away now to have that influence on this piece. It just has the leftover inertia, and we see that in all the pieces here in order for it to break. So, if you thought that glass couldn't bend, think again. Time warping changes the way we see the world because it makes the invisible visible.
Es geht los. 150, 148, 145, 142, 140, 135, 130.
Good. More energy.
There we go.
this is Maker J11, and in this video I'm going to show you some induction heating. I finally got around to playing around with some induction heating and making this video, so
today we are going to talk about resonance in AC circuits. This is something you actually use in your real life, because when you are tuning into a radio station, you're actually using resonance. Probably you know this, that a particular radio station transmits electromagnetic waves of a special frequency. So each radio station has its own frequency. Now while you turn the knob of the radio set, what you are doing is you're varying the capacitance of a circuit over here, and this in turn varies the frequency of the LCR circuit of the radio. Now when the frequency of the incoming waves from the broadcasting station match the natural frequency of the radio circuit, which is the frequency of this LCR circuit, then resonance happens. Now how do you detect that? That is the point at which the reception has maximum clarity and the current in the circuit is maximum at that instant. Now let's look at this a little in detail. If you recall, the impedance of an LCR circuit is given by Z equals square root of XL minus XC whole square plus R square. In case you are not familiar with this, I suggest you first go through the previous lessons, which is connecting an AC across a resistor, an inductor, a capacitor, an LCR circuit, and then come back to this lesson. Now coming back to this, the inductive reactance XL is given by omega times L, and the capacitive reactance XC is 1 over omega C. Now you can see that since both of them depend on the frequency omega, so the total impedance Z will also change with the frequency. See, if I draw a graph for each of them, now this is again something which has been discussed earlier, so in case you are not familiar, just go through it. This would be the graph for XL, since the inductive reactance is directly proportional to frequency. This would be the graph for XC, since the value becomes very low at high frequencies. This is not 0, it tends to 0. This is XC, and this is actually, the x-axis is actually an asymptote, so it doesn't really touch the axis. And the graph for the frequency would look like this, because the frequency doesn't change with, the resistance doesn't change with frequency. The total impedance Z, if I draw a graph, it would look like this. This is the value for, this is the graph for Z, and you can see that Z has a minimum value at a particular frequency, which I am going to call as F0. If we also recall the phasor diagram, then let's say this is the current in the circuit, this is the voltage across the resistance, this is the voltage across the inductor which leads the current by 90, and this is the voltage across the capacitor which lags the current by 90. Next, let's look at the impedance. The impedance Z is, the value of Z will depend on XL minus XC whole square and R square. You can see that at low frequencies the circuit is predominantly capacitive, and at high frequencies the circuit is predominantly inductive. Now there will be some value of a frequency in between when the capacitive reactance and the inductive reactance cancel each other out. This frequency is the resonant frequency. At resonance, only the resistance R contributes, because XL becomes equal to XC. So what you're left with, Z is equal to simply R, because this is root R square, which equals R. And at this instance, when the impedance of the circuit is minimum, the current which is given by V over Z will be equal to V over R. So the current will be maximum. See, because obviously if the impedance of the circuit is minimum, the current has to be maximum. Now if you are asked what is resonant frequency of an LCR circuit, that is the frequency at which the impedance Z of an LCR circuit is minimum. The resonant frequency is also known as the natural frequency of the circuit. If the frequency of the AC source that is driving the system matches this natural frequency of the LCR circuit, resonance occurs. For instance, in case of a radio set, say this is a radio set, now the incoming frequency is, say, let's say it has a particular value f, and the natural frequency of the LCR circuit of the radio omega is given by 1 over under root LC. This is because at resonance XL is equal to XC, which means omega L is equal to 1 over omega C, and omega square is 1 over LC, and this implies that omega equals 1 by under root LC. When omega is equal to 1 over under root LC, then since omega is 2 pi f, this can be written as 1 over 2 pi root LC. This frequency is the natural frequency of the LCR circuit, and we are going to denote this by F0. So when the frequency of the LCR circuit F0 matches the frequency of the incoming waves, which is F, which means when F0 becomes equal to F, in that case resonance is said to occur and the current in the circuit becomes maximum. So you might have noticed that the resonant frequency F0 depends on the inductor and the capacitor, but it doesn't depend on the resistance of the LCR circuit. It is independent of the resistance. But the resistance of the LCR circuit affects another very important factor, which is the quality factor. And we need to take a look at this in detail, because this tells us how selective is the circuit, what is the sharpness of resonance. So let's look at this a little more in detail. Let's say we have a circuit whose inductance is 2 Henry, capacitance is 0.5 microfarad, and hence the resonant frequency omega is 1000 radians per second. Now for different values of resistance, we'll plot a graph between the current amplitude and the angular frequency omega. which means as we vary omega, we want to plot the value of the current amplitude. When the resistance is 2000 ohms, which means it's a very large value, we get a graph which looks like this. Now you can see that at very low frequencies and at very high frequencies, the impedance Z is going to be very large, so the current is very small. The current is almost zero. Whereas at some value in between, which is the resonant frequency, and which in this case is 1000 radians per second, the value of the current has a maximum value. Now if we take a lower value of resistance, then what do we find if we draw the graph? Once again, at very low frequencies and at very high frequencies, the value of the current will be low, but the value of the current is maximum at a resonant frequency. See, if you recall, I is equal to V over R. Next, if we take a still lower value of resistance, then the value of the current at resonance is going to increase. So we have a higher value of the current at resonance. So now if we draw a graph, once again at very low frequencies and at very high frequencies, the value of the current is very low, and at resonance the value of the current is maximum. So this is when, let's say, the resistance is 200 ohms, and this is when the resistance is 500 ohms, and this is the case when the resistance is 2000 ohms. Now if you recall, at the beginning we talked about tuning a radio set where you're trying to match the frequency of the incoming waves with the frequency of the LCR circuit of the radio. Now this response curve determines how easily you can tune the radio set. See, if you have a high value of resistance, then the curve falls off slowly and the current doesn't change quickly as you move away from the resonant frequency. This means it's going to be difficult to tune in to a particular incoming frequency, because over a wide range of frequency, the amplitude of current is pretty much the same. It doesn't really drop off sharply. If you are not able to detect resonance, that means you will not be able to catch a particular frequency. So the circuit has low selectivity. But in case the resonance is sharp, then what happens? In this case, the selectivity is good. It is easy to tune in to this particular frequency because as you move away from it, the current falls sharply. See, we have two advantages. At resonant frequency, the current is very large, and as you move away, it falls off rapidly, which means at resonance you get a large current, which means at resonance the station will be very clear, and as you move away slightly, then the clarity becomes much lesser. So it's easy to tune into that radio station. Now if you want to give a numerical value to the sharpness of resonance, then that is called the quality factor Q. The quality factor Q is defined as omega naught by twice delta omega. See, omega naught is the resonant frequency. So this value is omega naught, and 2 delta omega is equal to omega 1 minus omega 2. And now how have we chosen these points omega 1 and omega 2? Omega 1 and omega 2 are on either side of the resonant frequency, and these are points at which the power in the circuit drops down to half. At the points omega 1 and omega 2, the average power in the circuit is half its maximum value. So these frequencies omega 1 and omega 2 are also known as half power points, the points at which the power falls down to half. In the circuits shown over here, Q for a circuit with the smallest resistance, which is 200 ohms, is more than Q for the circuit which has the largest resistance. So which means that Q for the 200 ohm circuit is more than Q for 500, and which is more than Q for 2000 ohm resistance. If you look at this expression over here, you will see that omega naught does not depend on resistance. But these two frequencies, which is omega 1 and omega 2, are going to depend on the resistance of the circuit. So the quality factor is affected by the resistance in the circuit. Now if you work this out and if you use some algebra, you finally get the quality factor Q as omega naught L over R. Now a circuit is more selective with a high value of Q, which occurs when the resistance is low or the resonant frequency omega naught times inductance is made large. Now the main points that we've discussed today is the resonant frequency F naught is equal to 1 by 2 pi under root LC. At resonance, the total impedance Z is equal to the resistance of the circuit. At resonance, the current becomes equal to V over R because the value of Z is R at resonance. The quality factor Q is defined as omega naught L by R. Just notice this is a dimensionless quantity. Higher the value of Q, more selective the circuit, which means a high value of Q gives us a sharp resonance and it responds to a narrow range of frequencies, whereas a low Q value responds to a wide range of frequencies and the resonance is not sharp. Here are a couple of questions to test your understanding. Try these questions. The answers are discussed a short while later. Now for the answers, the phase of the voltage is 0 degrees relative to the current. Resonant frequency depends upon L and C. The quality factor is, this is true because this is the same as omega naught L by R, since at resonance omega naught L is equal to 1 by omega naught C. Impedance is minimum at resonance and it is equal to R. Current is maximum and it is equal to V over R. Resonance occurs only in AC circuits and not in mechanical systems. No, this is false. This can also occur in mechanical systems.